Okay, now it's starting. Okay, I think we got it. All right, so today we're going to look at section 2.1 on tangent lines and rates of change. So let's first start off by looking at a given function. And so if you could take your highlighter and highlight this. So here is our original function right here. And we'll call this as our f of x. So what we're trying to do in this section is we're given a certain point. So here's the point at A, and the y value that goes with that is f of A, which is going to be right about here, f of A. And then here is a point, and we're going to draw a tangent line to this particular point and through this on the graph. So it's going to be this one right here. So this is the slope that we're trying to calculate. And so I'm going to label this as slope, and usually we use the letter M for slope, and then I'm going to write it as tangent as TAN. Okay, now the problem with this is that if you remember back in algebra, the way that you calculate slope is you need to have 2 points, right? So our slope general definition, back from when we had this in algebra, is you can think of it as change of y over the change in x. And that's the same thing as having 2 separate points and then taking your y value, subtracting it, and then taking your x value and subtracting it. So that'll be y2 minus y1 all over x2 minus x1. So the issue that we have with this formula is that you have to have 2 points. But if you look at this particular slope, you can see that it's only 1 point right here. Okay, so the way that we're going to resolve that problem is we're going to create a second point. So the point P is the point that we want, which is A, f of A. So now a little distance away, I'm going to call this point right here as my Q point. Right, so that's my Q point. And I'll call this as some x value, and then the corresponding y value is going to be right here. Right, so this is going to be my f of x. So at Q, my point is x comma f of x. And now I'm able to actually calculate what the slope is. So I'm going to refer to this as, they call this as a secant slope. That means that it's going through 2 points. So I'll say the slope of the secant line, and that is equal to, I take my y values, so f of x is my one y value, and f of a is the other one. So you have f of x minus f of a, and then divided by, and then I'll switch, divide it by the change of x values, so that'll be x minus a. So that represents this orange graph right here. But you can see that this slope of the secant line is not the same thing as the slope of the tangent line, right? So you have a slope of the secant line here, slope of the tangent line. There's some discrepancy. They're kind of going in the same direction, but it's not quite the same. So what do I have to do in order to make this orange graph, or this orange slope, similar to this slope right here is, I need to take this Q point, which is an arbitrary point, and I'm going to make it so that it is a little bit closer. So for example, instead of Q being right here, I could put it maybe right here, right? And then if I draw my secant slope, it'll be about here, which makes it a little bit better of an approximation. Now, what would make it even better? Well, I could take this point right here and move it even closer. So here is my Q point. So do you see that Q is arbitrary, which means that it can move closer and closer to the P point until it gets so close. I'm going to move it closer, 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 that we say it's almost landing on top of it. Okay? So what I have right here, for the slope of my secant line right here is exactly what is stated right here. Right? So this is kind of the estimation, but I need to do something more with that. So in order to make it a better approximation, I'm going to put this phrase limit as x approaches a out in front of it. Right? So right there. So what this does is it moves the Q point closer and closer to the P point. And so notice this f of x minus f of a all over x minus a is identical right here. Right? So that one and this one, they're exactly the same. So now the only difference is that this limit as x approaches a is placed in front of it. All right, so then it gets closer and closer, and then whatever the slope is for the tangent line, the secant slope is going to be almost the same, and in fact, as you take the limit, it's going to be exactly the same. Okay. I'm sorry you can't ask any questions, but you're doing a good job being quiet. And that's all being recorded. Okay, so now let's do a problem that relates to that. So it says to find the slope of the tangent line to the curve of f of x is equal to 2x squared minus 1 at x is equal to 1. So I'm going to set it up this way. I'm going to have a p point. So what is my p point? So they're specifically asking about x is equal to 1. So it'll be 1 f of 1. Okay, so that's my p point. And then my q point is the made up point that is some distance away, and I'm just going to give it a general point as x f of x. So my q point is x f of x. And now I'm going to set up my slope of my tangent line. So I'm using this equation right up here. And so I'll have slope of my tangent line, and that is equal to, so I'll start off with the word limit out in front. And then it's going to be my f of x. So here's my f of x. And then subtract off my f of a is f of 1. So I'm putting that specific point of 1 into it. So that'll be minus f of 1 all over. And then in the denominator, it's your change in x. So that'll be x minus 1. And then it's going to be as x approaches, and then it's going to get close to that number. So that's going to be 1. All right, so that's my main setup. And now I'm just going to plug it back into this function right here. So substituting this, that'll give me limit f of x is 2x squared minus 1. And then I can calculate what is f of 1. So what is f of 1 into f of x? I'm just going to put in 1. So that'll give me 2 minus 1. So that is equal to 1. So I'm going to subtract off 1. Right? So this right here, 2x squared minus 1 is my f of x. Minus 1 is going to be my f of 1, and then in my denominator I have x minus 1. All right, and then it's going to be as x approaches 1. And then I'll just solve it, or simplify it just a little bit, so it'll be a limit, and then it's going to be 2x squared minus 2 all over x minus 1. And then I'll attempt to do direct substitution. Okay, so you always have to do direct substitution at some point. So direct substitution here, ds, would give me, what is it when x is equal to 1? It'll give me 2 minus 2, so that gives me 0. And then the denominator, 1 minus 1, that gives me 0. Okay, which is called, you guys can say it, indeterminate form, exactly. So that tells us, signifies that we can continue and do some algebra with it. So then with that, you would have equals limit as x approaches 1. What technique would we use on this one? We've had 3 different types of main techniques. Factoring, yes. So I'm going to take out a 2, and then I have an x squared minus 1, so I'll just factor that again. So that'll give me an x minus 1, an x plus 1, and then in the denominator, I have an x minus 1. And hopefully that process is familiar because you guys have had that in the previous chapter. So cancel that, cancel, cancel. And then that gives me equals the limit, and x is approaching 1, and I have 2 quantity x plus 1, at which point I can do direct substitution. In other words, take the limit. So let x equal 1, so then that'll give me, and then drop the limit, so my answer is 4, and that gives me the slope of my, oh, it should be slope of the tangent line. Okay, so that's what it is in terms of the actual value of the slope. Let me clean that up a little. So this is going to be slope of the tangent line. Now I'm going to show you graphically what that is representing. So I'd like you to draw this right up here. So our graph is f of x is equal to 2x squared minus 1. So that is a parabola that is upward, and the vertex is at negative 1, 0, negative 1. So it looks something like this right here. And at 1, it's going to go to 1. So I'll just put a sketch there, and then you've got 1 right there. Okay, so then it's going to be a parabola that is up toward this way. Okay, so that is going to be my f of x. So what I've just found is this. So I look at when x is equal to 1, my point is right here. And then what I'm going to do is to draw a tangent slope. Right, so I'm just going to sketch it for now. So from here to here, it's got to just touch it at one point, from here to here. What I've shown in terms of my numerical answer is that the slope of this tangent line is equal to 4. Okay, so what does 4 mean? It means up 4 and then to the right 1. And with my very rough sketch, it looks like that is pretty much what it is. Right, now, this slope changes as I change my x value. So if I made my x value at 0, I'd have a different answer. If I made it at -1, I'd have a different answer. Right? So you're just calculating what is the slope at that particular point. Okay, so that's the part that we just calculated. All right, let's move on to an alternate way. So an alternate way to express the formula for the slope of the tangent line is to consider a point x f of x. So instead of our P point being a f of a, I'm going to call my x point x, or P point as x f of x. And then you're going to take some difference in the x direction, which can be expressed by either an h or a delta h. All right, so let's look at the diagram, and we'll just highlight the things that they're asking about here. So this time, here's your f of x going from here to here. That is my f of x. And now the point that I am considering is P, which is right here. This is my point. So here's my x value and then my y value, so there's a point. So eventually what I want to get to is this. I want to get to this slope right here. Right? So this right here is a slope of my tangent line, but I have the same problem as I mentioned before. In order to do slope, I have to have 2 points. So what I'm going to do is create another point. So I'm going to call it as my Q point, some distance away. Right, so this time, instead of saying this is a separate point, I'm using this delta x, which is exactly the same thing as what h is. Okay, so just write delta x is equal to h. And so from the given point, I'm going to move a little distance away from there. So x plus delta x is going to be this point that is the Q point for the x. And that is equivalent to x plus h. Right, so that point right here. And then what matches up with the y value is going to be your f of x plus delta h, and that is the same thing, or delta x, so that's the same thing as saying f of x plus h. Okay, so then I'm going to write out my 2 points on that. So I have my 1 point. This time my P point is going to be x f of x. And then my Q point is going to be, I'm going to use the h version on this, right? So it's that point plus a little distance away, so that's going to be h, and then comma f of x plus h. All right, so here is my point I want, and this right here is the newly made arbitrary point, and now I'm going to state my slope. Okay, so here is my slope, which is slope of my tangent line is equal to, it's going to be, put the word limit out in front of it. And so you'll have your change in y, so that is f of x plus h minus f of x. And then in the denominator, you have x plus h minus x. Now, this time, instead of making this point get closer to this, I want to close in on this gap, right? So if this is a distance, so let's just use a number, for example. Like say that it was 1 unit away. What would you have to do in order to close this in so that it's a better approximation? Someone can say. Like, say that this is 1. What would be better? Maybe like a half? What would be better than a half? 0.0, 0.0, or 0.1, 0.01. So eventually, this gap, we'll call it as h, becomes what? 0. So that's why you have it as h approaching 0. Okay, so that's a little bit different concept as we are looking at here. Here you're letting x go to that value a. Here you're making h go out to 0, right? And so you have almost what we need up here. I've derived it. And what happens in this denominator is your x's cancel out, so that cancels out with this. So then you just end up with this, and that is your main formula for the second part. Okay, so the slope of the tangent line. And in this one, the only difference is that instead of h, they're putting in delta h, delta h, delta h, and delta h, right? But they use h a lot more than delta h, or delta x. I meant to say delta x on all of that. And so this is the more familiar one. Okay, so let's try that one with this problem. So let's start off with our 2 points. So our first point is our P point, which is our given x value, so that's going to be 2f of 2. And then our Q point, this time we're going to look at from 2, and you're going a little distance away, and so we represent that by 2 plus h, comma, f of 2 plus h. Okay, so that's going to be our main set. So you always need to write out your P and your Q. And then I'm going to now set up using this equation here. So what is the slope of my tangent line? That is equal to, I have my limit out in front, and then I just do change in y, so that'll be f of x plus h. Oh, actually it's 2. Made a mistake here. Okay, so this should be a 2 since we're starting it at 2. So 2 plus h minus f of 2, and in the denominator, no matter what number you have, those will always cancel out, so the denominator will just become an h, and this is as h approaches 0. Okay, so now I'll substitute that in. So our value right here is the following. So this 2 plus h right here is going to go back into this x right here. All right, so what is f of 2 plus h? It will be equal to the limit as h approaches 0. So this will become a 1 over, and then I put in 2 plus h wherever I see an x. So that'll be 2 plus h, and then I still have my minus 1. Okay, minus 1, and then it's going to be minus, calculate f of 2. So what is f of 2? F of 2 is going to be 1 over 2 minus 1, so that's just going to be 1. And then you have minus 1. And then in your denominator, you'll just have an h. And then simplify it just a little bit. So I'll just simplify this portion right here. So that gives me the limit as h approaches 0. So this part right here is going to come out to be 1 over h plus 1 minus 1 all over h. And direct substitution actually never works, right? But I could just do that in my head and show you that I get what? 1 over 1 is 1. 1 minus 1, 0. And the denominator is 0, so you get 0 over 0. Okay, so what technique do we have for something like this?
Complex fraction.
Yep, I have a complex fraction. Multiply top and bottom by h plus 1. So h plus 1. So then if I distribute that through, that'll give me limit. And this times this gives me a 1. And then this times this, I have to distribute the negative. So that'll be a minus h minus 1 all over. And then don't multiply this denominator out. You just leave it exactly like that. So it'll be h and then quantity h plus 1 as h approaches 0. And then you get things to cancel out. So this will cancel out with this, cancel, cancel. And then I have my h here, which will cancel out with this h. And so I'm left with overall, in the numerator, I have a negative 1. And then the denominator, I have a h plus 1 as h approaches 0. Okay, now I take the limit, which means that I'm going to let h go to 0. So this right here now goes to 0. So my answer comes out to be a negative 1, and that represents the slope of my tangent line. So that would be my answer there. Okay, I'm going to stop recording now.